So this is Ron Cote. Ron used to run marathons, but not anymore. In 2005, he had a spinal cord injury, and his legs are partially paralyzed. He's determined to walk again, but as you see, after years of physical therapy and hard work, he still cannot quite make a step with his left foot. Now, these soldiers in Afghanistan, they have a problem too. In 2001, when they went into the mountains, they had to leave their vehicles behind because the mountain trails were too narrow and too rocky. And in fact, the Battle of Tora Bora was unsuccessful, partly because we couldn't move enough people and equipment into those mountains. Both of these problems can be solved by robotics. And since 2001, the Department of Defense has spent hundreds of millions of dollars on development of robotic technology for walking. And here's one well-known result of that work. It is the so-called big dog robot. It can carry about 150 pounds, and that's obviously a great help for soldiers who are traveling on foot. Another example are these robotic exoskeletons that can give soldiers extra strength and endurance. And smaller versions of that have been developed for people with disabilities. And one of those is the Indigo exoskeleton that's developed by Parker Hannafin here in Cleveland. So these are very impressive technologies. But before you get too excited, I want you to take a good critical look at this. And one clue is right here in front of you. This Sarcos exoskeleton is powered by a giant hydraulic pump, and it receives the power through a hose. So if you wanted to take this into the mountains, you would definitely need a very long hose. The big dog robot doesn't need a hose. It has a gasoline engine on board, but it has other limitations. Its top speed is only 4 miles per hour, and even at such a slow speed, it doesn't get more than 4 miles out of 1 gallon of gasoline. Even a Humvee gets better gas mileage, and it can easily go 10 times faster and carry 10 times more weight. If this big dog robot has to go on a 100-mile trip, it has to carry 25 gallons of gasoline. That's just about all it can carry, so that's obviously not very practical yet. And this may surprise you, but there is a far better technology that already exists, and it has existed for hundreds of years. And here is that technology. It's horses. Horses are perfect for narrow trails and uneven ground. They also have impressive technical specifications. They can carry about the same load as a robot, but they run a lot faster. And if you look at the food that they consume and you convert it into the equivalent amount of gasoline, it turns out their fuel economy is about 100 miles per gallon or even better. So think about it. Here we have an animal that can travel 6 times faster than the best robot we have, and it uses only 1/25 of the energy. And it gets even better because horses don't actually have to carry their fuel. They can just eat plants that grow by the side of the road. So I know what you're thinking now. Why didn't they use horses in Afghanistan? And of course they should have. That wouldn't have taken 10 years or $100 million to get going. And if that solves the problem, why should we even do research on robotics, right? Well, my answer is I truly believe that robots are going to be better in the long run, but we need to get a lot smarter about how we design them. And as a starting point, I suggest we take a good look at horses and why they work so well. So I'm now a professor in mechanical engineering, but I actually started my scientific career in a veterinary school, and I studied anatomy and movement of horses. On my first day there as a graduate student, my professor, Fritz Hartmann, he took me into the anatomy lab, and we worked on dissecting a horse leg. And at one point, we took the leg off the table, and we moved the joints. And that's an experience I never forgot. And to share that with you, I made a little mechanical model. So horses have just about the same joints that we have. This would be the hip and the knee and the ankle. And the foot is very long and vertical, and it never touches the ground. This is the toe. And horses actually stand on the toenail of their middle toe, believe it or not. So look what happens if I flex the knee joint. All the other joints are flexing at the same time. The other thing this leg can do is that if you lock the knee joint, you can put weight on the leg and you push it down and it won't collapse. And the reason that all of this works is that you have these long tendons here. They cross multiple joints and they're perfectly arranged to coordinate all these movements. That is a beautiful mechanism that horses have developed over millions of years. And you can see this mechanism in action when horses run. Because of these coupled joint motions, the hoof is always perfectly positioned when it hits the ground. And the movement looks smooth and easy. And that's because it really is easy. Most of the work is done by the tendons, as I've just shown. And the muscles don't need to do much. And that's really the secret why horses get 100 miles per gallon and why they never stumble, even when they're tired. My work now is in human motion, not in horses, but this knowledge has still been very useful to me. About 10 years ago, I was preparing a lecture on muscle mechanics, and I was trying to explain to the students why our muscles and tendons are attached to our bones exactly the way they are. And I remembered how beautifully that design was in the legs of horses, and I asked the question to myself, what if you could attach tendons anywhere you wanted on a human leg? Could you make walking easier? Of course, we can't redesign human legs, but we can attach extra tendons on the outside. But where? That's a mechanical design problem, and I solve it the way mechanical engineers do, making a computer model and running thousands and thousands of simulations with all these combinations of attachment points, and each time calculating how much that would help the walking movement. And one solution that came out is this one. And it looks a little bit like a horse leg. So you can attach an elastic cable to the front of your waist, run it all the way down your leg, and attach it to your heel. And it has to go around these pulleys that have to have a specific size. And based on my calculations, this could do about half of the work that's required for walking. So if you would wear this outside your body, walking would get 50% easier. And this is now commercially available, and it's known as the Kickstart walking system. And Ron was one of the first users. And with that device, he can now make steps with both of his legs, and his walking speed is quite good. This elastic cable gets tensioned exactly at the right time to help him lift his heel and swing his leg forward. And that's something he couldn't do in all those years since his injury. Now, that's a system that can help you move. It's not quite a robot yet that can move on its own. A robot would need motors. And based on what I told you earlier, you might think that that would then automatically become something very clumsy and inefficient. But there's some good news. If you use electric motors, you can do some of the same things that tendons do in the leg of a horse. And here's a little demonstration that you can actually do at home if you have a couple of Lego motors lying around. So there are two motors, and there's no battery here. They're only connected by this electric cable. If I move one motor, it will produce an electric current that goes through the other motor and will make the other motor move in exactly the same way. Look at this. So there's no mechanical coupling, there's only an electrical coupling. This is precisely what happened in the leg of the horse when I moved the knee and the other joints started moving. So these ideas are a very important part of some research that we're currently doing in the Washkevich College of Engineering. And I'm working on that with two colleagues, Dan Simon and Hans Richter. And the project is called Optimal Prosthesis Design with Energy Regeneration. And so as of today, this is our prototype of a prosthetic leg. And it will have two motors, one in the knee and one in the ankle, and is for above-knee amputees. And the switches that connect these motors They are controlled by a computer to direct the energy flow and to control the motion of the leg. So switches in this cable can be used to disconnect these motions. So when we don't want these motions to be identical, we can switch that off. And that's already an improvement on animals, because animals can't really switch their tendons on and off that way. You can also, in this system, if one motor produces more energy than the other one needs, you can send the extra energy into batteries and capacitors and store it for later use. And you can switch other elements in and out as needed. The possibilities are really only limited by our imagination, and it can all be controlled by software. And if we do this well, we can build a leg that does everything that a human leg can do and use almost no energy. So these are exciting times for robotics and for using robotics to help people with disabilities. Robots are still very far behind animals, but now that we can understand the principles of animal design, we can start to catch up. And we can even improve on nature by using those same principles in new ways that nature never imagined. Thank you.